Madam, start பண்ணலாம்.
Sir, we will start, sir. Once again, I welcome you all for this afternoon session. Sir, you can continue, sir.
Okay, thank you. Just a minute, I'll just present my slide, okay? Just a minute.
Sir, have you shared your screen?
No, not yet. Just a minute.
Oh, okay, sir. Okay.
Okay, so I think the screen is visible.
Yes, sir. Yes, sir.
Okay,
Visible, sir.
okay, okay. So we were discussing about the principal component analysis. Okay, so the main idea of principal component analysis is to reduce. Okay, so you can see reduce the dimensionality of data set by retaining the variation present in the data set. Okay, so you want to retain the variation, at the same time reduce the dimension. So that is possible through your SVD. Okay. Okay, so this is the same is done by transferring the variables to a new set of variables which are known as principal components. So like what we said about sigma 1, sigma 2 like that. Okay, and are orthogonal ordered such that the retention of variation present in the original variable decreases as we go down the order. So this sigma 1 will be greater than equal to sigma 2 will be greater than equal to sigma 3. So which means the variation is reducing as we go down. Okay, so you stop at particular k, okay, and you just take that, whereas the rest k minus r you ignore. Okay, right. So this is so in this way the first principal component retains maximum variation. So this will retain the maximum variation. Okay. So this is what actually I have already done. Okay, so I will not go there. Okay, now I come to the another type of machine learning algorithm that we generally do. This is linear discriminant analysis. Okay, linear discriminant analysis. What is this linear discriminant analysis? Say you, for example, you take this particular data set. Okay, so here you see that the variation along this axis, okay, is more. Okay, along this axis it is more. Okay, and this is more, but along this axis it is less. Okay. Now what happens when you project this? So the variation along this axis is more. Okay, this, along this is more, whereas this is less. So what we do is we project this data into this axis. Okay, so when you project this complete thing. Okay, so what you get is this. You get this. So this is the principal component. sigma 1, sigma 2, where sigma 1 is greater than sigma 2. So in that case, when you project it along the axis, which is having major variation, okay. So in that case, you find that it becomes like this. And what happens is, as a result, you see in 2 dimensions, this was clearly separable. In 2 dimensions, this data set was clearly separable, linearly separable. It loses the linear separability. Okay, you lose the linear separability. Here now, you see that the green ones and the red ones, they are mixed up and they are not linearly separable. Okay, so by applying PCA, principal component analysis, what we get is we forego the linear separability. Okay, so instead of that, what we want to do is we want to have both. Okay, so we want to have retain the linear separability, at the same time reduce the dimension. Okay, so how we are going to do that? So that is what is called the linear discriminant analysis. That's what we are going to see. Okay, now you see the same, you take the same data set. Okay, the data set what we have shown here. Okay, and if this is a principal component, okay, for this data set, if this is the principal component, what I call sigma 1, and when you drop your map, okay, your data points onto that singular component, okay, so you find that there is no linear separability here. Okay, now what you do is you take the perpendicular line to this, okay, and then you drop it. Okay, then in that case, if you do, then you find that they are linearly separable. Okay, so you find that what you are doing is you are finding the major principal component, then you are taking something which is perpendicular to that principal component, and you find that now you see that there is a clear linear separability between these 2 classes. Okay, right. So find projection to a line such that samples from different classes are well separated. That's our that's the aim of linear discriminant analysis. Okay, so how will you measure that? Okay, so how will you measure that? For example, here what you do is, say for example, you have say this mu tilde 1. So mu is the mean. So mu 1 is the mean of this particular data, that is the red one, and mu 2 is the mean of the second one. Okay, now you take these 2 components. Okay, this is the vertical component and the horizontal component. Okay, and you project your data on both. You find that this mu 1 becomes mu 1 tilde here and mu 2 tilde here, whereas when you project it onto the vertical component, this becomes mu 1 cap and mu 2 cap. So here it is cap, mu 1 cap, mu 2 cap, but whereas on the vertical component it is mu 1 tilde and mu 2 tilde. Okay, now what is that you observe? Okay, so how good is this mu 1 minus mu 2 tilde, mu 1 tilde minus mu 2 as a measure of separation? Okay, the larger is this separation, the larger is the difference between mu 1 tilde and mu 2 tilde, better is the expected separation. So you find that the expected separation is better if this difference between mu 1 tilde and mu 2 tilde is large. But whereas the vertical axis better line than the horizontal axis to project for class separability. Okay, now you see that the problem crux of the problem comes here is that this mu 1 cap minus mu 2 cap, okay, that this difference is greater than the difference between mu 1 tilde minus mu 2 tilde. Okay, so in that case what happens? So you cannot take this difference, the absolute value of the difference between the mean values, okay, of the 2 mean the difference between the 2 mean values, that you cannot take, because on the vertical line it shows good separation, but on the horizontal line shows poor separation. Okay, so that's one more thing that you have to take. Okay. So the problem with mu 1 tilde minus mu 2 tilde is that does not consider the variance of the class. We have not considered the variance of the class. See, you see here, the variance of the class is less here in this direction, but whereas the variance on this is more. Okay. So it doesn't consider the variance of the classes. Okay. So that's how the Fisher linear discriminant analysis, they have just worked out a sample. Okay. You have a set of points here. Okay. So you can see that the blue ones and the red ones. Okay. So in a 2-dimension, so I can call it say x1, x2, and these are the points. Okay, on the dimensions. Okay. So class 1 you can represent as a pair of points like this. Class 1 is 1, say this is 1 comma 2. Okay, say this is 1 comma 2. Okay, so like that. Okay, this is 5 comma 5. Okay, and similarly class 2 1 comma 0, this is 1 comma 0. Okay, so like that you just put it. Okay, arrange the data in 2 separate matrices. Notice that PCA performs very poorly on this data, because when you find the principal component is generally, this is the component, the principal component, and you find that it is poorly separated. Okay, because the direction of the largest variance is not helpful for classification. Okay, it is helpful for dimensionality reduction, but it is not helpful for classification. So linear discriminant analysis, what you have to do, you have to do. So here you have to find just this line that is perpendicular to this class. Okay, and you find that when you, so this was your PCA, and this line is your linear discriminant analysis. So on this you find that you will, when you project it, you will find that they are, the blue ones will be here. So the blue ones will fall here. And the red ones are here. Sorry, this is blue. Okay. Now you see there's a separability between this set of classes and this set of classes. Okay. So this is how LDA differs from this principal component analysis. And the morning somebody asked about the references. So these are the references you can have. So this is a good book on mathematics for machine learning from University of California, Thomas, written by Thomas. And then as far as linear algebra is concerned, this is a better book. Okay, Introduction to Linear Algebra by Strang. And so in the, after 2 days, I think I will be taking one more session on probability. In that case, this will be a better book for probability, Rosenthal. Okay, so these are the books, and other books are also there. Okay, so you can take, so this slide I will be sharing with you so that you can take it. Okay. Okay. Now we have just completed the morning part of it. So in the afternoon part of it, I will be getting into 2 topics. One is the convex optimization. Okay, and next one is the optimization problem. Another one is the support vector machine, introduction to support vector machine. So these 2 topics I will be taking in the afternoon session. And what I plan to do in the afternoon session is just I will go through this topic, and I want to present you one more example for this application of this eigenvalue eigenvector problem. Okay, so that I want to discuss with one more example, real-time example, so that you will know, appreciate that how this matrix theory and this eigenvalue problems are really helpful. Okay, in our machine learning or any other scientific applications. Okay, so this is what I want to do in the afternoon. So now for the time being, so this slide is over. So just I will close this slide. Okay, so just a minute, I will present again. Just wait for 1 minute. Okay. So just I will take this, I'll get to the next problem, that is optimization problem. Okay. So in optimization problem, actually, so this is again another important topic in machine learning, optimization. Okay. So in optimization, what we do is we are given with a function f of x. Okay. And our job is to either minimize f of x subject to some constraints, or maximize f of x subject to certain constraints. Okay. So it will be either a minimization problem or a maximization problem. Okay. So now, so where this C is a set, what we call it is as a constraint set or feasible set. Okay. So I will tell you what is that meaning. Okay. So graphically, when you want to look at it, so it will be something like this. Say, for example, you have a two-dimensional space in which you have some contours. So contour, you know that this is a surface. Okay, on this surface, this is the error function value. So actually, the errors are more here, and this is the minimum point. This is the point where it is you get this is x1, x2, and this point is x1 star, x2 star, meaning that is the optimal point. Okay, that's the optimal point, this point here. Okay, whereas any other point if you take, it will be more, the value, this is a contour. You know what is the help of a what is a contour? Okay, so when you look at it in the other dimension, it will be something like this. Okay, so the contour is, this is the point, this is the point, and these are contours. Okay, the contours are like this. Values are the same at a particular height. Okay, and I am looking at from the top. When you look at from the top, it looks like this. Okay. Now the minimum point is this. This is the minimum point. Okay, this is what we are interested to find. Okay, but what is happening is this problem is unconstrained. This problem is called unconstrained. Why is unconstrained? That is because we just want to find the minimum value. We are not imposing any constraint. Okay. Okay. So we say that this solution is what we want, and there's no other constraint on that. Now suppose you want to make a constraint satisfaction problem, constraint optimization problem. In that case, what you do is you have to take, say for example, this is your straight line you are taking. You just say that this line. Okay. Now this line is a straight line, and this line has some equations. Say for example, x1 plus x2 something equal to c, some equation where we are not or I will use some other way. I'll just take another. I'll take this. Now it is x1 plus x2 equal to some c. Okay. So this is the line. Okay. Now you want to find the minima. You want to minimize this function. This function, this surface. Okay, is a function f of x. So we want to minimize. We want to minimize f of x. Okay, subject to x1 plus x2 equal to c, and x1 greater than or equal to 0, and x2 greater than or equal to 0. So this is the constraint. Now what is that meaning? Now which is your minima point? Okay. Now this is no longer your solution. Okay, because this is a minima. Of course, this is a minima, but actually it is not lying on this line. So our constraint is that x1 and x2 can take a values which are only on this line. Okay. So in that case, what you have to do? Which are the 2 points? In that case, the 2 points are this and this. Okay, so this and this, they fall on this particular contour. So therefore, my solution will be these 2 points. Okay, and this is a contour. Therefore, these two are the valid solutions. Okay, so this one may be x1, x2. This one may be x2, x3. Sorry, x3, x4. So these are two solutions which have the same minimum value because it falls on the contour subject and also falls on the line. Okay. So this is what is called constraint. There is a constraint optimization. Okay. Now there are several questions here. The questions here are that given some certain constraint, given certain function, okay, given certain function, what is that actually that decides whether a feasible or an optimal solution can be found, whether an optimal solution can be found or not. Okay. So this is what actually the problem is. Okay. Now I think you have understood what is constraint satisfaction problem. And another thing that you have to know in this constraint satisfaction problem is that convex functions. You should know something about convex. So what is a convex function? For example, if I take y is equal to x square. Okay. Now that is looks like this. So this is x, this is y. I say y equal to x square means as x increases, so y is equal to x square. So it is a curve like this. If x decreases, if x is negative, even then y is positive because if x is negative, then also it is positive because we take in square. So then in that case, it's like this. Okay. Now if you take this region, what is this region? This region is a convex region. So why I say it's a convex region? Because if you take 2 points, for example, if you take 2 points on this region, say I take a point here, I take another point here. I just join them by a line. Okay. In that case, if this two, then all other points on this line. Okay. So this is one line. I call it x1, y1, x2, y2. This is one point. This is the other point. I join them by a straight line. Then all the points on this straight line, if they fall in the same region, if all the points on this particular line happen to be in the same region, then I can say that this is a convex region. Okay, this is a convex region. Now, for a change, you take this region. This region you take. This region is not a convex region. Why? Because you take a point here, you take another point here. I will say this x1 dash, comma y1 dash, another point here, x2 dash, y2 dash. Now you try to join them. In that case, you find that this from this point to this point, the points on this line, they do not fall in this region. They fall in the other region, but they do not fall in this region. So therefore, the blue region, what I have put a blue stripe. So the blue region is not a convex region; it is a concave region. It's a concave region. Right. So this is what you have to remember. Okay. So convex functions are this. So how do you say that it's a convex function? Say, for example, if you have a function, you take a value lambda that is greater than 0, not equal to 0, sorry, if a lambda, that is small lambda is greater than 0, then lambda times f of x plus 1 minus lambda times f of x should belong to S, where S is any region. For example, this is a region S, then for that function, lambda times for any 2 points, lambda times this function into 1 minus lambda times the function should be belonging to the same S. So this is what is called a convex function. Okay. So this you have to remember, because in the case of optimization, convexity of a function plays an important role. Okay. So this is what I told you about constraint optimization and unconstrained optimization. So now we'll go to the next one. Okay. So constraint optimization is the previous one was a unconstrained optimization. Constraint optimization is you have to still minimize the function subject to constraint. You are given a constraint. For the previous case, this was not there. Okay. And so why I have put less than or equal to 0? Okay, because when you look at this here, so what is this region? This region, any point on this red line says y is equal to x square. Okay, and any point inside the region is y is, if you take a point here, y is greater than x square. Okay, so inside this region, the value of y will be greater than x square, whereas outside the region, value of y will be less than x square. Okay, so therefore this line says, therefore what is the constraint? The constraint says here in this case that some function of x which is less than or equal to 0. Okay. Okay. So now you have to classify the problems that you are given minimizing function f and a set of constraints. Okay, we call them a linear programming problem. Okay, so you see that methods are available, mathematically methods are available to solve optimization problem if they are linear. Okay, linear meaning that f and g should be linear, they should be linear functions. But whereas in our case, f is not a linear function, f has a quadratic value, f is not linear, but g is linear. Okay, like if here in this case. In this case, f is not linear, but whereas this g is linear. Okay. But if both f and g are linear, then we call it a linear programming problem. Linear programming problem, and you have a lot of tools available. You have something called Lingo, you have MATLAB. So you have procedures available that easily you can solve the problem. If the problem is not linear, if the function is not linear, if the problem P1 is not linear, then we call it a non-linear programming problem. So, so this is slightly different. Okay. So if any one of them, for example, if this and this, if they are not linear, like what I have shown in our example, this was not linear, but whereas G was linear. So in that case, we call it a non-linear programming problem. Okay. And in the nonlinear programming problem, if the function happens to be of power 2, for example, if the function happens to be of power 2, like for example what I have given here, in this case, like the second example, yeah, here I have given that y is a square of x, that means it is quadratic. So it is non-linear, but it involves power 2 square, so it is quadratic. So such functions are called special case of non-linear functions, so we call it quadratic. Okay, that is quadratic. So quadratic QPP, quadratic programming problem is different, is a special case of non-linear programming problem. It's a special case of non-linear programming problem. Okay. Now given, when you are given function, now how do you say it is convex or say if f and g is the set of constraint functions, so you can have more than one constraints also. If f and g are convex functions, then we call convex functions what I defined before. Okay, so f and g both are convex functions, then we say that the problem is a convex programming problem. So for convex programming problem also we have softwares available, methods available, which you can directly solve using our MATLAB or Lingo. Okay, and in that case, there are different types of convex programming problem. That one is that this, depending upon this. Suppose you are doing a minimization. You are doing a minimization, and your function you are trying to minimize is convex, and the constraints are also convex. Okay, then we call it a convex programming problem. Okay, in that case, g of I should be less than or equal to 0. Okay, if minimizing f of x and all g of I of x is less than or equal to 0, then f and g of I are convex, then we say it is a convex programming problem. Okay. Now coming to the next thing, that is here. You are trying to maximize. Now you are not trying to minimize. You are trying to maximize, but you see that the g of x is still less than 0, and in that case, this will be a convex programming problem, provided f is concave. F should be concave. In that case, we are trying to maximize, f should be concave. Okay, and g of I should be convex. This should be convex. This should be convex, and this should be concave. Okay, and it should be a maximizing function. Okay, so in that case, we say that still the problem is a convex programming problem. Okay. So when do you say optimization problem is convex programming problem? Then in that case, it should be a minimization problem. In that case, f and g should be convex. If it is a maximization problem, in that case, f should be concave and g should be convex. Next is here. Now here you see that if it is a minimization problem, okay, and the constraints are greater than 0, constraints are greater than or equal to 0, then f is f is convex, f happens to be convex, and g happens to be concave. G happens to be concave. Then also we say that this problem is convex programming problem. Okay. And another thing is, you are trying to maximize f of x, where all the constraints are also greater than or equal to 0. In that case, f and g both should be concave. F and g both should be concave. Then also we can say that this function is a convex programming problem. Okay. So this is, so we have seen that definitions. Okay, we have seen the definition. So what are the definitions? What is a linear programming problem? What is non-linear programming problem? In the same way, among non-linear programming problems, if the power is 2, okay, quadratic, then it is a quadratic programming problem. For all other non-linear programming problem, they have to be a convex programming problem. They have to be convex. Only if there is convex, we can solve using ready-made tools. Okay. So in that case, that's what we are doing here. So you have to see whether it is convex. So how do you say, once you are given a problem, minimize something, some constraint, then looking at the function, looking at the constraint, you can say that whether the problem is a convex programming problem. Okay, if they satisfy this condition. If they don't satisfy this condition, then we say that that is not a convex programming problem. Then you cannot use standard tools for solving those problems. Then you have to approach for some other, say our neural networks or some other approach. Okay. Right. So this is what is about the optimization problem. Okay. So like for example, here, if you take minimize x1 plus x2, okay, and similarly subject to some constraints. Okay. So looking at this constraints, you will know that this is something like a circle, is it not? x1 square plus x2 square less than or equal to 4 is a circle. Okay. Because you know the equation of a circle, and so this is x1, 2. So this is x1 square plus x2 square less than or equal to 4. That means the region inside. If it is greater than 4 means the region outside. Okay, so this you have to, this is a constraint, and what we have to minimize? We have to minimize x1 plus x2. x1 plus x2 is simply a line. Like this is x1 plus x2. How? If x1 increases, x2 should decrease, because this is constant. X1 plus x2 is constant. So if x1 increases, x2 should decrease. If x2 increases, x1 should decrease. Okay, so this is the line. Now what we have to minimize? We have to minimize. So now you know that this is the constraint, and this is the function. And looking at this function, you say that this function is a convex function, because diagrammatically you can see that f is convex. Sorry, this is g, Ilya. G is convex, and f is linear. F is linear. F is this. This is f. This is f. This is g. F is linear, and linear is actually supposed to be convex, because a region on this side is convex, a region on the other side is convex. So when a function is linear, it is both convex and concave. Okay. So what you can take is, you can take f as also convex. Okay. So f is convex, g is convex, and you are trying to minimize. So the problem is a convex problem. So problem 1 is convex. So if you take problem 2, here also the f is actually linear. F is linear, and yeah, but this is maximizing. You are trying to maximize. When you are trying to maximize, f is linear, and this is convex. So this is, both are convex. But you are trying to maximize. So you can refer the previous slide. When you are trying to maximize, both cannot be convex. So f should be concave. Okay. Here f and, in our example, f and g are both convex, and we are trying to maximize. That means what? It is not convex. Our problem is not convex programming problem. So our program P2 is not convex program. Got it? So this is what actually you have to do. Okay. So I will not go deep into it, because it is not possible to cover the complete thing in a thing. So just I will give you the gist of this. What do you mean by optimization, and what are the terms that come in optimization? Okay. And here you see, this is a quadratic programming problem, which you can simply put it in a matrix form. This is how they have put in a matrix form, because in matrix, x into x transpose is x square. Okay, x into x transpose is x square with some q. Okay, and the q is a symmetric matrix that you have put here of order n. So in a matrix form, this is how quadratic function will look like. Okay, so this is a quadratic term, and this is the linear term. Okay, in ordinary case, it will look like this. In ordinary case, it will look like this. So this is quadratic, this is linear. Okay. So the same thing, but in a matrix form, it looks like this. Okay. In a matrix form, you have to put it like this. So this is your minimization function, and this is your constraint function. Okay, constraint. Okay. And there are some results actually, I think, which you can use, actually says that a quadratic program problem is convex. A quadratic programming problem is convex when q is an objective when q in the objective function, when this q in the objective function is positive semi-definite matrix. So what do you mean by positive semi-definite matrix? Is when you take the determinant of the matrix, it should be either equal to or greater than 0. Okay, if the determinant of the matrix is equal to or greater than 0, then the matrix is said to be positive semi-definite. If that is the case, then we can say that by just looking at this q value, okay, if it is positive semi-definite matrix, I can immediately say that this is a convex programming problem. I can just like that I can say it's a theorem. Okay, so the proof of the theorems are actually involved, so we'll not get into that. So when you say a quadratic problem is convex, we can say that if the Q involved in the matrix is positive semi-definite. Okay, so based on that, there are some operations, there are some examples that are given here. Okay. Okay, so I think I will just so why I am just telling you about all these things is classification of the optimization problem and other things is you have a set of tools that you can for linear programming problem, that is for LPP is very easy. It's actually you have a tool very easily you can do, but for other non-linear programming problem, especially quadratic programming problem, if they are convex programming problem, then we can solve those problems provided we satisfy some condition, and that condition is called Kuhn-Tucker condition. If some conditions like called Kuhn-Tucker conditions are met, okay, then we can say that this problem, this nonlinear programming problem or quadratic programming problem can be optimized. If these conditions are not met, then we cannot say that this program can be solved by a standard. So if this is available, then we can use either MATLAB or you can use your what you call Lingo. Okay, so for solving, we have standard methods. You can use these standard methods and solve the problem. Okay. Right. Similarly, for constraint optimization problem. Okay. So this is what I told you, the Kuhn-Tucker conditions. So these are the Kuhn-Tucker conditions. So provided these Kuhn-Tucker conditions are solved or conditions are met, then we can say that you can find a point x bar, which is a local minimum point on the problem at which basic constraint qualification holds. Then there exists some KKT multipliers, that is Lagrange multipliers, such that the following conditions hold. So if you have these conditions are called Kuhn-Tucker conditions. If these conditions are true, then we can say that there is a local minimum point that is available for a non-linear programming problem. Okay, where this del refers to the derivative of that particular function. Okay, since we are putting in a matrix form, we are writing it in a we are using the del operator. If it is a single variable, then we will be using you'll be using ordinary differential equation. Okay, but this is for multi-dimension, we are using this particular. Okay, so these things I will not go much into it. Okay, so I think with this I can wind up this optimization problem. Okay, next I will get into the other problem, that is our problem of support vector machine. So, we have so just now I introduced you about linear programming problem, quadratic programming problem, and convex programming problem. So actually, there is a particular paper by Mangasarian which has introduced an approach called mathematical programming approach. Okay, the advantage of using this method is that most of the problems involved in machine learning results in linear programming or quadratic programming or convex programming. Okay, and the Kuntukar conditions and the duality theory are applicable to handle such problems. These are methods that are available to solve such convex problems. Okay, so because of that, when you are aware of this, when you can say, given a problem, if it is linear or quadratic or convex, and if you know whether those Kuntukar conditions are satisfied, then we can use this method called mathematical programming approach to solve the optimization problem without having to go for our heuristic methods like or nature inspired methods. Okay. If the problem doesn't fall under this category, then naturally we have to go for other types of approaches. Okay, this is already we have seen. And support vector machine, the main advantage of support vector machines over other methods is that it results in a convex programming problem and always has, you can always obtain a global optimal solution. So the advantage of a support vector machine is that if the problem happens to be a convex programming problem, okay, then we are guaranteed to find a global optimal solution. Okay, whereas in any other optimization problem, it is not always guaranteed that whatever you find, it will be a local minima, but not a global minima. Okay, but if the optimization problem happens to be a convex programming problem, then we can say that what we get is a global minimum. Okay, so this is yeah. Now we'll see something about linear separability. Okay, linear separability. So this, say for example, this is set of points. Okay, and this is another set of points. Okay, then you see that this line can linearly separate. This line is Wx equal to b. Okay, where W is the weight vector. Okay, Wx equal to b will be equal to this line can linearly separate the two samples. Okay, linearly separable. But whereas this is a problem where they are not linearly separable. Okay, where this function f is not a linear function. Okay. Now there is a theorem again which says if you are given some points, how do you say that they are linearly separable or not? Okay, says that let A and B be two sets. Okay, this pink one, sorry, violet one and the blue one. They are some finite sets. Now you want to know that all the points in this set, the purple one, they are one class, and the set of points in the blue one are another set of points. You want to know whether these two sets are separable or not. When I show it diagrammatically, you can immediately say that they are not separable because this is a common place you have. Okay, but apart from that, there is a theorem that says if A and B, these are two sets, and if the convex hull are disjoint, if the convex hulls are disjoint, then it is linearly separable. If the convex hull is not disjoint, it is not linearly separable. Okay. So what do you mean by convex hull? So convex hull is actually say for example, you have a set of points. I will just mark with one color. Okay, this is one set of points. Okay. Now, what is a convex hull? So, what is the convex hull? Just take these set of points as points on a plane. Okay, like you put some nails. Okay, on this, and you take a rubber band and just stretch a rubber band over this nail. Then what will happen is this is how it comes. Okay. Now these points are the points on which you have put a rubber band. Okay, and these 2 points are automatically enclosed within this region. Okay, now these points is what is called the convex hull. Okay, convex hull. Now you suppose you have another set of points. Say I will use the red color. Now you take the convex hull of this red color points, and now you see that the convex hull is this. You take a rubber band, if you stretch it and put it on them, then these points are automatically enclosed. Okay, now this red one is also convex hull of the red one. Now look at this. Are they disjoint? Yes, they are disjoint. They are not overlapping, disjoint. So therefore, when the convex hull of one set of data points and the convex hull of the other set of data points, if they are disjoint, then we can say that this class is linearly separable. We can linearly separate. So you have algorithms to find the convex hull. Okay. So given a set of data points, you can find the convex hull, and then you can say that whether they are linearly separable or not. If they are linearly separable, then we can always find a line that can linearly separate. Now just take this condition. For example, I just modify this like slightly. So you have 2 points here. Okay, but you have one more point here. Okay, now you take the convex hull. Okay, so the convex hull will look like this. From here, so these points I can erase. There's a point here. Okay, now you see that this is a region where the two convex hulls, they are overlapping. Okay, and therefore this set of points, these two set of points, they are not separable. They are not linearly separable. Okay, so that's the essence of this theorem. Says that these set of points, a plus, a minus, a plus are positive points and a minus are the negative points, are not linearly separable since their convex hulls are not disjoint. See, here you have some overlap. So not here. So here you have some overlap. So because of that, so what is happening is you can say that this problem is not linearly separable. Okay, and for that we have to derive some feature. So that is you have to say the inequalities that is the set of points, the positive set of points should be greater than some EB. Okay, EB is this point. Say for example, if the purple ones are here, then the line is this. The line says this W transpose X equal to B. Okay, and if the points happen to lie above that, then they will be greater. If and negative points are those for which the points are below. Okay, and on the line there is no point. On the line there is no point. So this is the inequality of linear separability. Okay, this is inequality of linear separability. And for our mathematical purposes, what they have done is they have put it in this form. Okay, so the same thing, but what they have done is they have taken this a plus. They have taken this EB. Now this is greater. Now they have just put a plus E. Okay, and they have made it greater than or equal to. So because we want our because in our optimization problem we always want the constraints to be greater than or equal to or less than or equal to. So to change that, they have made it like this. Okay, so where by they have what they have done is by suitable scaling, what they can do is they can make this inequality greater than inequality as greater than or equal to. Okay, like that. So just by adding here, it is greater than, this is greater than this, but when you add something, so what happens? It may become equal to. Yeah. So you have to do some scaling. Okay. If this is less than this, when you subtract something from this, it becomes equal to. Okay. So the same thing, the same amount you are adding there and the same amount you are subtracting here, so that you get the margin. This is 36. Okay, I will take it. Okay. So this is what we have done. Okay. Right. And once you have done this, once you have put it in this form, then what you are doing is you are trying to put it. Say we are trying to put it in this form in an optimization problem perspective. Okay. So you take all the points, positive points. This a plus is all positive points, and a minus is all negative points. Positive means the class is yes. Negative means the class is no. Okay, it's a binary classification problem. And what they have done is the binary classification problem they have converted into an optimization problem. Okay, that's the thing. And what they have done is they have put the equation in this form, and then what they have done is they have put it in this form. Okay, so they have taken this this one this side. Okay, and similarly these two on this side. When you take this one this side, what happens? It becomes minus a plus w plus eb plus e. Okay, that's what you get here. Minus a plus w plus eb plus e. And here when you take this eb minus e this side, it becomes a minus w minus eb plus e. A minus w plus minus eb plus e. And what you have to do, you are taking the average of that average and you are trying to minimize. Okay. And now what you do, your problem is this classification problem, what we have shown here, sorry, in the previous slide, is reduced to a optimization problem. Is reduced to a optimization problem. Okay, right. And now you see that you can just write it that minimize this subject to these conditions. Okay, then which is a linear optimization problem. It's a linear optimization problem and it can be solved easily using MATLAB or Lingo. Okay, so what we are trying to do is we are trying to frame classification. We are trying to frame a classification problem as a optimization problem and trying to solve it with a standard tool. Okay, right. The standard tool is available for this. Okay, right. Now here you see that we will take the example of and or problem, XOR and problem and XOR problem. So you know that and XOR. Okay, so and is something like this. This is input x1, x2, 0, 0, and this is 0, 1, this is 1, 0, and this point is 1, 1. Right. Now, what is the value of AND? When you take an AND gate, AND. When you take an AND gate is 0 else everywhere, except when both are 1, it is 1. Okay. Now, when you do this, so the same, so 1, 1 is a positive point because when both inputs are 1, this is a positive point. So I'll take this as a plus. And when any one of the input is 0, 0, 1, 0, 0, or 0, 1 or 1, 0, these three inputs, they are taken as a minus. So these three come under a minus. Now what is that you have to do? You have to classify a plus and a minus. Okay. So how do you do that? So the same thing is put in a form. So this is you have only one point. Okay. So y1 plus there are 3 points here. Z1 plus Z2 plus Z3 divide by 3. So the mean. So that's what actually the formula actually we saw here. That is, you have to take divide by the number of points. So the number of points is M1, M2. Here it is 1. M1 is 1. M2 is 3. So here 1 by 3, and you are just adding the points. Okay, and subject to the condition. What is subject to the condition? Subject to the condition is this. Okay. That is, you have to put it in this a plus w minus eb plus y. So when you put it in that form, then you see that these are the conditions you get. Okay, these are the conditions you get, and where W1, WB, they are unrestricted about the sign. You can use any sign for them. But whereas your Y1, Z1, Z2, Z3, they should be greater than 0. They should be greater than or equal to 0. With this condition, so the AND problem is converted into a linear programming problem, which you can solve using a standard procedure, for which you find that, these are the values you will get, and you will get an optimal solution. You will get an optimal solution. Okay. Right. If on the other hand, if you take an XOR problem, the XOR problem is little different, because here in this XOR problem, what you will do is, this is 0, 0, 1, 0, 0, 1, 1, 1. Now the XOR problem is slightly different. When both inputs are 0, output is 0. When both inputs are 1, also output is 0. But when any one of the input is 1, other is 0, then the output is 1. Sorry, the output is 0 when both are equal. When both are not equal, then the output is 1. Now here, this is a little tricky problem. So how do you represent this? Okay. Now here you see there are two positive points. These two are the positive points, and these two are the negative points. So two positive points, what are they? 1, 0, 0, 1. 1, 0, 0, 1. They are the positive points, and negative points 0, 0, 1, 1. Okay. And this you have to convert it into a classification problem. This you have to convert it into a classification problem. That is, you want to classify the inputs as whether it's because you know that it's not linearly separable. This is not linearly separable. So you find that if you cast this problem into the same problem like what we have done before, you will find that the optimal solution is this value, and here you get z equal to 2. Okay, right. This value, the value of z becomes 2. Thus, this, so which is not minimum. So therefore, this is not a linearly separable problem. Whereas in the previous case, z was 0. Here, when in the case of AND, the z was 0. This value of z, minimum value of z was 0, because you cannot have we cannot have other values, because the binary problem. So the value is 0 or 1. So the value of z can be 0 or 1. 1 is if z is maximum. 0 means there is minimum. So here you see that here the value, you get a value of 2, which says that this problem cannot be solved. This problem cannot be solved. Why? Because it is not, what is that? It is not linearly separable, right? So this is how actually we are trying to cast. Okay, and this is on the definition how our linear, what you call this support vector machine works. Okay, so it tries to find a margin. Okay, tries to find a margin, and that margin is given by this value, that is 2 by the Forguenes norm of W. Okay, W is the vector. Sorry, W is the parameter that actually separates your. In case of 2 dimension, it is a line. In case of 2 dimensions, a line. In case of 3 dimensions, it will be a plane. Okay, that will separate your two classes, and the width of the margin is given by 2 by W, by the norm of W. Okay, 2 by norm, because W is not a W is a vector. Sorry, is a matrix. Therefore, we have to take a Forguenes norm. So 2 by norm of W is the width of the matrix, width of the path. Sorry, the gap, and whatever points that lie in this region, it's called a dead zone. It's called a dead zone, and the points that lie on either side. Okay, because this is W transpose X equal to B. This is W transpose X equal to B minus 1, and this is B plus 1. Where the minus 1 and plus 1, they are that nothing but E, the value E what we have shown here for inequality purpose. for inequality purpose, we have shown this E. Okay. So that E is what actually that 1 plus 1 is. And now the points which are on that particular line, that is W transpose equal to V plus 1 or W transpose X equal to V minus 1, they are called the support vectors. These are called support vectors. And all other points are set here set to be less than this B minus 1, and all the points here are greater than, sorry, these are less than B plus 1, and all the points here are greater than B minus 1. Therefore, those which are equal to B minus 1, they are falling on that particular boundary. Okay. So this is called the margin. Okay. So this is how, and in our SVM, support vector machine, we always try to increase the margin. We always try to increase. We want a classification, but at the same time, we want to increase what? 2 by W norm. When you want to increase this, that's why the support vector machine is also called a large margin classifier. Okay. So now there are two objectives are here. One objective is to increase the margin. Other objective is to minimize the value. Okay. So there are two objective functions which come into SVM. Okay. So this is what I said, the margin. Okay. Right. Now what is that you have to do is you have to find a optimal separating hyperplane. Okay. Okay. So what is an optimal separating hyperplane? Optimal separating if the margin is maximum. If the margin is maximum, then we call it as a optimal separating hyperplane. So this I will skip because it is not necessary. It's an additional theorem which we have to do, but may not have. Then I'll come to the last slide. In this slide, you will find that yeah. So how to find the soft margin classifier? So soft margin classifier is where you are actually interested in finding a optimal hyperplane. But here you see that this, you find that there are two samples, positive samples here and one negative sample here. Okay. So now what is that? This could be a linear, this could be a what you call outlier. Okay. The problem is linearly separable, but you see that there are some outliers. If you ignore these outliers, then it is linearly separable, like here. Okay. So what you have to do is, therefore it is called a soft margin classifier. Okay. So what we try to do here is, we try to have this function. So this is what our problem is. Okay. Now this is, we want to minimize the error also. See, we want to maximize the width. This width we have to maximize. Okay. At the same time, we want to minimize this error. This error. Okay. So the error is given as epsilon. Okay. The error is given as epsilon. Okay. This is a set of errors and multiplied by a constant. You give a weightage for that. And this is the W, I told you, no, 2 by W norm. 2 by W norm. So 2 by W norm should be maximized. That means 1 by W norm by 2 should be minimized. Okay. Our objective is to maximize margin. So maximize margin means I have to increase 2 by W norm. Okay. But W norm is nothing but 2 by W transpose into W. Okay. I want to maximize this, which is same as minimize W transpose W by 2. Okay. So if I minimize this, it is same as maximizing that. And at the same time, I should also minimize my error. Sum of error with a constant weightage. C is a weightage constant I give. Okay. So this, now I have put my problem as a optimization problem here. Okay. Subject to the constraint. Okay. Right. and the constraint also I add the for each point I add the error. Okay. Now, if you solve this problem, then it becomes a soft margin classifier. Okay. Right. Now, here, what is the purpose of C? That's what you ask. Tell me, if C is large, what will happen? If C is large, actually the problem is minimizing problem. You want to minimize this expression, the entire expression you want to minimize. But if C is large, that means you are focusing much on the errors. You are focusing much on the errors. Okay. If C is small, then you are focusing much on the margin. Okay. That's what that controls C. That in the support vector machine you have this parameter C, is it not? The C parameter actually tells you how much. If C is equal to 1, then we are giving 50% weightage to the maximizing of the margin, and 50% weightage to the minimizing of the error. Right. So this is what actually the in short the support vector machine is. Okay. Support vector machine is in terms of optimization problem. Okay. So that's other things. I will not go into the details because this is a bit involved. Okay. So now look at this figure. Now you can say that once you have done a soft margin classifier, now you see that what does these different data points say? From here, this point number 8, okay, you see it is a misclassification. Similarly, this point number 3 is also a misclassification. Okay, point number 3 is a misclassification. Point number 8 is a misclassification. But whereas point number 1 is correctly classified, point number 7 is correctly classified, point number 6 is also correctly classified. Okay, point number 5 is also correctly classified, but it falls on the dead zone. Okay, but whereas point number 2 falls on the support vector. Okay, so like that. So that for that the different conditions are given here. Okay, so here if the error is 0, if the error is 0 means the point is correctly classified. Okay, if no error means point is correctly classified, and this alpha is equal to 1. The alpha is some value. Okay, some value you choose. If it is equal to 0, then it is correctly classified. If the error is 0, but the alpha lies between this 0 and C, is alpha is not 0, alpha is some value that is between 0 and C, then it is a support vector. That is a support vector. If alpha is equal to C and you have error greater than 1, then we say it is not classified. So it is not correctly classified. So another way you can say it is not correctly classified is here. So where you see that alpha is equal to C and the error is greater than 1. Okay. So in that both the case you say it is misclassified or not correctly classified. Okay. Whereas if the error is between 0 and if you have error which is 0 between 0 and 1, okay, that means the error happens to be in this line, that is it is between this margin in that case, and alpha happens to be it is correctly classified, that is bounded support vector. It is correctly classified, that means this point. So what is it? Fourth point. Fourth point is there. The fourth point. So fourth point and fifth point you will find they are for which you have error, which is between 0 and 1. Fourth point and fifth point, you find the error is between 0 and 1. Okay, and you see that alpha is equal to C, but still they are correctly classified. Okay, but if it is greater than 1, error is greater than 1, and alpha equal to C, then it is not correctly classified. That you can straight away say. Okay, error is 0. But alpha is equal to 0, then correctly classified, like this case. Okay, if alpha value is between 0 and C and error is 0, still it is a free support vector machine. So it is a free support vector. That is point number 2 and point number 6, they are support vectors. Point number 2 and point number 6, they are support vectors. So this is what we do. Point number 2 and point number 6, they fall on the support vector. Okay, so this is how actually in short you can construct a support vector machine. So support vector machine, to conclude, say that what is the advantage of support vector machine is that if the function you are trying to minimize happens to be a quadratic problem, quadratic programming problem, okay, then it is possible to find what do you call, sorry, it is a, sorry, not quadratic, it is, if it is a convex programming problem, if your function happens to be a convex programming problem, then support vector machine is bound to give you a very good global optimum, okay. So, and that is what we have seen, and what we have done is support vector machine, which are used, generally used for classification. The classification problem, we have typecast the, we have put the problem in a different manner, typecast the problem as a optimization problem, okay. That is converting one problem to another type, okay. That's generally we do in algorithms also. Suppose if a solution is available in one problem, if you have a new problem, convert the new problem into the old problem and solve using the old tool, okay. So the classification problem is converted into an optimization problem, provided the function is a convex function. Then we can use our convex programming models to solve the optimization, to solve the classification problem. That's what support vector machine is all about, okay. So I think with this I can cover my topics what I wanted to cover in this today's class, okay, and still I have some time. So what I thought was I want to give you some real feel, okay, about the eigenvalue, eigenvectors, okay. So this is not part of this, actually I'm again going back to the morning session, so where I will be talking about an application. I'll just take an application and I'll let you know that how this eigenvalue helps us in our real-time applications, okay. So I'll just take one example. This is not from machine learning, okay, right. So just I will let me present one more presentation. Yeah. So just I will just go fast, okay. So on this so don't bother about other things, okay. Just I will tell you what it is. So here you see that we have a diagram, okay. It is about a bird, okay, a bird whose population we are interested in. For example, you know that we are interested in the population of tigers, because tigers they are you know that they are being killed, and over a time you will find that the tigers will become extinct. So generally ecology people, they will be always interested in to know about preventing the extinction of animals, okay. They don't want the diversity of the planet to get lost, okay. So we should always prevent animals from getting extinct, and in that case, so you find that this is an example of a bird whose age is 3 years. The bird lives for only 3 years, okay, and in the first year the bird does not breed. Actually that means the bird does not lay eggs in the first year. When the bird is 2 years old, more than in the interval 1 to 2, in the interval 1 to 2 years, the bird can lay eggs. How many eggs it can lay? It can lay 5 eggs, okay. And in the period 2 years to 3 years, the bird can lay 4 eggs. So when a bird lays eggs in the period 1 to 2 is young, so it can lay eggs. So it lays 5 eggs. So the 5x, they again go to the year 1, because when the eggs hatch, this goes to the age 0 to 1. Okay, so that's why there's an arrow showing here. And when a bird which is 2 to 3 year old, when it lays an egg, 4 eggs, one bird can lay 4 eggs. In that case, those 4 chicks, they will come in the first year. Okay, so 0 to 1. So this is about the reproduction. This backward loop is about the reproduction, and the forward loop is about the death. For example, a bird which is say 0 to 1 year old chick, small chick, for it to come to second year, that is when for it to come to the second that is to complete the first birthday and go to the second year. So only 15% of the birds survive. Means there are 100 birds here in which are 1 year old. When they want to go to the second year, only 15% go. What happens to the rest? The rest are eaten by some other animals, rest are by disease or something. So the birds die. So only 15% birds go to the second year of age. And from second year of age to third year of age, only 50% birds go. What happens to the other 50? The other 50, they die out of some maybe climate or some other thing. Okay. So this tells you about the death of the birds, and whereas this tells you about the increase of the population. So this is decrease of the population, increase of the population. Now you have 4 parameters: P1, P2, F2, F4, F3. Now what you can do is you can put this in an equation form like this. Okay. So this means that at time t, 5, because why? What is the 5? 5 is the 5x and 4 is the 4x. Okay. So the number of birds in age 2, lay 5x. So 5 into x2 at time t plus 4 into number of birds in age 3 at time t equal to number of birds in x1 at time t plus 1. So t is, you can count t in terms of years. Okay. So this is one equation which tells you about the increase, how x1 increases, and other one is how the different birds die. For example, from x1 to x2, from x1 at time t to x2 at time t plus 1, the number of birds which reach this stage is very low. Okay, so it is say only 15%. 15% of x1, they go to x2 at time t plus 1. And similarly, 50% of birds in x2 at time t go to x3 at time t plus 1. So these 3 equations are given. Now these 3 equations, I can put it in a matrix form like this. These 3 equations, I can put it in a matrix form like this. Okay. So when you just multiply, this is the equation in a standard form, and this is in matrix form. When you multiply, you get the same equation. Okay. So now this matrix is a special matrix. We call this a Leslie matrix. Okay. Now what is the advantage of this Leslie matrix? You have the Leslie matrix. Now at time t, if you know the population of birds, where x1 is the number of birds which are 1 year old, x2 is the number of birds which are 2 year old, and x3 is the number of birds which are 3 year old. When you know this number and you multiply by this Leslie matrix, then you get the number of birds in the same 1 year, 2 year and 3 year at time t plus 1. That is, if you are given the data at this year, next year I can predict how many birds will be there from each thing. So like this, if you then what you do, you can use this here to get a time t equal to 2. Then again you can substitute, resubstitute again and again, because this is a recurrent equation. You can just first time you use first time you use x0, you get x1. Next time you use x1, you get x2. Next time you use x2, you get x3. Likewise, you can do for 100 years. Okay, and now you can at the 100th year, x of say at 100, you can tell what would be the population which are 1 year old, 2 year old or 3 year old. Okay, so this you have to do a repeated manner. Okay, so that's what I have shown here. Okay, this is what I have told you. So you start with this initial distribution. Okay, initially there are 300 birds in the first year, 440 birds in the second year, 350 birds in the third year. Now when you repeat this for 100 times, you find that you find a surprising fact here, that right from after say 9 onwards, you find that this percentage is the constant. You see, it's constant. Why it's constant? That means 82% of the birds are 1 year old, 12% of the birds are 2 year old, 5.91% birds are 3 year old. So this remains constant. Even though the number of birds will differ, but the ratio of 1 year bird to 2 year old bird to 3 year bird, they remain constant. Okay. So this means the population stabilizes. This means the population stabilizes. Okay. That means the bird will not get extinct. That's the meaning. Okay. But you need not have to do this for 100 times to know this. What you can do is you can do a very good task of finding the eigenvalue of this matrix L. Just take this matrix, find the eigenvalue. So it will have 3 eigenvalues, 3 by 3 matrix. So I have eigenvalue 1, 2, 3. You have to take the dominant one. You have to take the biggest eigenvalue. Okay. If there is a biggest eigenvalue, then you are guaranteed that this population will not die. If this eigenvalue lambda 3 happens to be less than 1, okay, not equal to 1, sorry, less than 1, then I can say that every year the population will be decreasing. If the population will be decreasing, and finally the population will become extinct. Whereas if lambda 3 some dominant value is greater than 1, then we can say that the population will keep on increasing. The population will keep on increasing. If the lambda value is equal to 1, then I can say that the population will remain constant. But this never happens. So either we will be here or we will be here. Okay. So if you find a lambda value, the eigenvalue that is greater than 1, then the population will survive. Okay. Whereas if the lambda value happens to be less than 1, the population will become extinct. So that is so without doing anything, just you take the matrix, you take the eigenvalue, you are able to predict that. Okay. So that's the beauty of it. So you can see that in this case, in our case, the lambda value was just 1.02, means greater than 1. And therefore, the birds, they will have a healthy population. Okay. But whereas, if the lambda value is between 0 and 1, the birds will become extinct, or birds or any other animals will become extinct. Okay. So this is actually why I wanted to tell you this example was to let you know that the importance of, because we have been always using this linear algebra, we have been always using eigenvalue, eigenvector, but without knowing the real implication of those vectors. Okay. So I think with this I can close my session. Okay. So if any clarification is needed, we can discuss. Okay. Or we can discuss offline, because I have a meeting to attend today. Okay. So I will just thank the organizers for their and the participant for patiently listening to the 2 hours, sorry, in the morning, and of course another 1.5 hours in the afternoon. Okay.
Thank you, sir. Thank you, sir. On behalf of myself and on behalf of all the participants, I thank Dr. R. Thangarajan, Professor and Head, Department of Information Technology, Congo Engineering College, for provided the in-depth knowledge in linear algebra, which is crucial for understanding how machine learning algorithms actually work. And also he discussed a topic about optimization. It is also an important part of machine learning and deep learning algorithms. So this session gave a better perception of how these algorithms really work, and also he gave a foundation for deep learning. Thank you, sir.
Thank you so much. Thank you, madam. Thank you, participants. Thank you.
Thank you to all the participants for your patient listening. So here we will share the feedback link in the chat window. So kindly fill your feedback form. So while you fill the feedback form, you fill the faculty that is participation code correctly. So tomorrow's session starts by 10 a.m. in the topic of artificial neural network, which is handled by Bipul Kumar from industry. Thank you.